Okay, in this lecture video, we're going to talk about compounds that form ionic bonds. And ionic bonds happen between cations and anions. And the way that it works is that you have some atom that's going to transfer some of its electrons, particularly its valence electrons. And when it does so, it becomes a cation because it's losing these electrons. It's transferring them somewhere else. And it's transferring them to another atom into its valence shell. And when that atom gains the electrons, it becomes negatively charged to form the anions. So the bond happens when one atom transfers its electrons to another to form the cation and the anion that then one another because positive and negative charges are attracted to one another. So even though when you form these cations and these anions that interact with one another, and each one of them individually has a charge, a positively charged cation and a negatively charged anion, the net charge on the ionic compound that's formed is 0. Net charge on ionic compound is 0. So that means there's enough positively charged cations to cancel out the negatively charged anions. That also means that the number of electrons gained by the anion has to be equal to the number of electrons lost by the cation. So just like with atoms that you can't create or destroy them, you can't create or destroy electrons. If they're being transferred from one chemical species to form a cation, they're ending up somewhere else. First thing we want to talk about is how do we identify ionic compounds? And we can make a little bit of a chart for that. So in order to have ionic bonds, the first thing that must be true is that you have to have a cation and you have to have an anion. So you have to have a positively charged species and a negatively charged species. You can have multiple ones of each in order to get a net charge of 0, but you have to have cations and you have to have anions. So when you're looking for the cations, they can take two forms. The first form is you can have a monoatomic cation. So that means it's a cation made out of one atom. And if you have a monoatomic cation, then it must be a metal. So you can look for metals in these compounds. The second thing you can look for then is polyatomic cations. So polyatomic cations, remember, are cations that are composed of multiple multiple atoms. Those you just have to recognize. You have to be able to look at a grouping of atoms and say, oh, that's a polyatomic ion. You want to identify anions in much the same way. So your anion can be monoatomic, so consisting of one atom. And if it is, that anion must be a non-metal. Okay, so metals never form anions. They only form cations. And then like cations, your anion might also be polyatomic. Sorry, I have an iPad mini. It's a very tiny screen. So you can learn to recognize these anions that are made out of multiple atoms. So this is sort of the flow chart for how you identify whether or not a compound has ionic bonds. So let's look at a bunch of examples. 0. Oops. Show that the cation and anion charges always cancel each other out. So the way that we're going to do that is we're going to have a little equation, and we're going to say the number of cations that you have times the charge on the cation, that has to be equal, I didn't finish, plus, let's write that better, so we're not confused. So plus the number of anions that you have times the anion charge, that has to. So let's look at some examples. So our first example we'll look at is NaCl. So looking at the periodic table, we can start identifying, or I could tell you at this point, that there is one sodium cation. We can tell that from the subscript here, or lack thereof. So if there's no subscript shown in a chemical formula, it just means there's one of them. So we have one sodium cation times the charge on the sodium cation. And then we have one chlorine anion, or chloride anion, times its charge. That has to equal 0. So in this case, we have one single positively charged cation and a negatively charged chloride anion, and those charges cancel each other out. So let's look at another example. Let's look at calcium chloride. So calcium is a +2 cation, and chloride is a -1 anion. And we can see here from the formula that there are two of them. So I'm going to draw one calcium cation. Here's one chloride anion, and here's the other one. So just from looking at this, you should recognize that you have a +2 charge here, and it's canceled out by 2 of these -1 charges. But we could write that with our formula saying that there's one calcium ion times its charge of +2 plus 2 chloride ions times their charge, each of -1, that equals 0. Okay, more examples. Let's take calcium oxide. Calcium is a +2 cation. Oxide is a -2 anion. One calcium cation times its charge of +2 plus one oxide anion times its charge of -2 equals 0. So they cancel each other out. Let's do another. We'll start to up the level of difficulty. Potassium carbonate. So in this one, we've got 2 of these potassium cations, each of which has a charge of +1. And then you've just got to start practicing recognizing these polyatomics. So since this has a metal, potassium is a metal, metals always form cations. So then you know that everything else has got to be an anion. And since there are multiple atoms, a carbon and 3 oxygens, you have to recognize it as a polyatomic. And then you just got to realize that it's carbonate, CO3, with a charge of -2. So then we can write down that there are 2 potassium ions times the charge on each one is +1. And there is one carbonate anion times its charge of -2. So don't get confused here by this 3 subscript on the oxygen. That just means there's 3 atoms of oxygen in the entire carbonate. But as a whole, there's only one carbonate anion. So this equation then works out to equal 0, as it should. Let's do the reverse example with a polyatomic cation, NH4Cl. So in this case, you don't have a metal to give this one away. So you just have to recognize that NH4 is a polyatomic ammonium cation with a charge of +1. Then chloride must be our anion. It's got a charge of -1. So 1 ammonium times its charge of +1 plus 1 anion times its charge of -1 equals 0. Then we've got 2 more big examples as we up again the level of difficulty. Here's another one with the ammonium that we just did, and also a polyatomic anion. So the parentheses and the subscript of 2 here is telling us that we have 2 of these polyatomic ammonium cations. So I've got 2 NH4 pluses in this compound, and everything else must be my anion, so I've got 1 SO4 minus 2, that's sulfate, it's anion. So now if we write our equation, we've got 2 ammonium cations times the charge on each one is +1, plus 1 sulfate anion times the charge on it, which is -2, that does in fact equal 0. Now, why do we keep doing this, you ask? We're just keep proving over and over again that the net charge on an ionic compound is 0. But that does matter because pretty soon we're going to use this equation to figure out the charges on cations or anions. And we've got to know that this is true in order to take names and write the formula so that we know how to combine these cations and anions into the correct chemical formula. So let's more example here. We'll take CuCl2, and it turns out if you look at your periodic table, copper is a transition element. So that means you can't predict its positive charge. You know it's a positive charge because it's a metal, but sometimes copper forms a +1 charge, and sometimes copper forms a +2 charge. So we can't tell just from looking at this, but we could figure it out knowing that the net charge on the compound must be 0. We also know that since there's no subscript here, that there must only be 1 of these copper ions. So we know that 1 copper cation times its charge, and we're just going to call it X because we don't know what it is, plus 2, right? We got 2 of these chloride anions. And each chloride anion, we know based on its location in the periodic table, forms an anion of charge -1. That has to equal 0. So if you solve this equation, x minus 2 equals 0 for x, you get that x is +2. So that means the copper in this particular compound is copper +2.